Welcome to This Explainer. Today, we're basically playing the role of weather detectives. We're going to uncover the invisible, behind-the-scenes levers, both geographical and atmospheric, that actually determine the climate of literally any spot on Earth. So, have you ever spun a globe and just wondered, why is it that two cities sitting at the exact same latitude can have wildly different temperatures? I mean, one could feel like a complete tropical paradise, while the other literally demands a heavy winter coat for half the year, right? It's a classic meteorological mystery, and honestly, it sets the perfect stage for our investigation into the planet's hidden temperature controls. All right, here's our roadmap for today. We'll be looking at principal controls, the latitude lever, altitude and air density, nature's cloud blanket, land versus water, and finally, invisible winds and cities. Let's get into it. Section 1. Principal temperature controls, the suspects behind local climates. Okay, here's the full lineup of our primary suspects, the primary temperature controls we'll be investigating. Notice how we're starting on this massive planetary scale, right? Things like latitude, altitude, and global cloud cover. And then we're going to zoom all the way down into regional effects. We'll look at land and water heating differences, ocean currents, the jet stream, local winds, and eventually the highly localized impact of the actual cities we live in. Moving right along to Section 2. The latitude lever, moving from the equator to the poles. So the absolutely crucial thing to grasp here is this concept of insolation. It sounds complex, but insolation is really just the incoming solar radiation that hits our planet, basically sunlight. And because the Earth is, a sphere, this incoming radiation is directly affected by a location's latitude. The specific angle of the sun dictates whether a place is continually warm, like the tropics, seasonally variable, like the mid-latitudes, or just continually cold, like the poles. Tracking annual temperatures across different latitudes reveals a really clear pattern. If you look at Salvador, Brazil, near the equator, the temperature line is almost completely flat. It's continually warm all year round. But watch what happens as we move up through places like New Orleans, Edinburgh, and Montreal. The lines start curving into these massive seasonal extremes, right? And then they drop all the way down to that freezing, plunging curve of Barrow, Alaska, up at 71 degrees north. So latitude, it truly sets the entire climatic stage. Section 3. Altitude and air density. Climbing the climate ladder. Now, why are mountain peaks freezing cold even when they're sitting right in the middle of the sweltering tropics? Well, let's look at a tale of two cities in Bolivia to isolate the effect of altitude. Both of these cities sit at the exact same latitude, roughly 16 degrees south. Now, Concepcion sits at a low elevation, about 490 meters, and it enjoys a wonderfully warm average annual temperature of 23 degrees Celsius. But check out La Paz. It's perched way up high in the Andes Mountains at over 4,100 meters. Even though it receives the exact same solar insolation, the same exact sunlight, its average temperature drops drastically to just 11 degrees Celsius. And this atmospheric density chart pretty much solves our mystery. As we climb higher, air density and pressure drop significantly. Up in the troposphere where La Paz sits, the air molecules are just spread really far apart. And this thin air simply has a remarkably low ability to absorb and radiate sensible heat, which is exactly why you'd still need a heavy winter jacket in La Paz despite being so close to the equator. Less dense air means less heat trapped. It's as simple as that. It causes those cold temperatures and a much wider daily temperature range, completely regardless of your latitude. Section 4. Nature's cloud blanket, the sky's thermostat. Get this, at any given moment, about 50% of the entire Earth is wrapped in clouds, which brings up a really fascinating, kind of contradictory question for us. Why do clouds cause cooler days but warmer nights? Just think about that for a second. They're the exact same clouds, acting like nature's automated thermostat, and yet they produce entirely opposite effects depending on the time of day. Here's how it works. During the day, clouds have a high albedo. That means they act like massive white mirrors, reflecting shortwave solar radiation away from the Earth. They bounce a huge percentage of it right back out into space, which cools the surface down. But at night, the whole process flips. The Earth is trying to emit heat back out into space, and those exact same clouds absorb and re-radiate that long-wave Earth energy straight back down toward the surface. They trap it, effectively keeping us warm like a giant blanket. Moving to Section 5, land versus water, the tale of the coast and the desert. When we actually compare continental and marine conditions side by side, the physical differences are pretty stark. Land is opaque, meaning the sun's energy only heats the very top, shallow layer of dirt and rock. It also has a lower specific heat and literally zero mixing between layers. Because of this, continental landmasses heat up rapidly and they cool down just as rapidly. Water, on the other hand, is transparent. That allows solar insolation to penetrate much deeper. It also has a higher specific heat, meaning it takes way more energy to warm it up. Plus, because water is mobile, it mixes constantly in these vast ocean currents, so oceans warm and cool very, very slowly. And we can't forget that marine environments have much greater evaporation, which uses up a lot of latent heat. To really see this dynamic in action, let's compare the temperature graphs of these two locations. Check out the incredibly stable, moderate, almost perfectly flat temperature line of San Francisco on the coast. It's totally marine regulated. The nearby Pacific Ocean acts as this massive thermal buffer. Now contrast that with Yuma, Arizona. Surrounded entirely by continental land, it experiences wild, extreme temperature swings day after day, warming up and cooling down super rapidly. The land just simply cannot hold on to thermal energy the way the ocean does. All right, final section. Section 6, Invisible Winds and Cities, the final variables. We absolutely have to talk about a major player in global weather patterns, the jet stream. So, what is it? It's this irregular, highly concentrated band of westerly wind flowing high up in the atmosphere. You can think of it as an invisible river of air. It's created by the friction of the Earth's rotation combined with all that unequal atmospheric heating we've been tracking today. By constantly steering these huge weather systems and air masses across the globe, the jet stream acts as a phenomenal, totally dynamic temperature control. Now, these westerly winds aren't just a constant force. They actually vary dramatically by season. The jet stream is generally pretty weak during the summer, but man, it roars to life and becomes incredibly strong and influential during the winter months. And looking at the globe as a whole, the polar jet stream up north is typically much stronger and way more dominant than the subtropical jet streams sitting closer to the equator. Finally, we have to turn this investigation back onto ourselves. Let's look at the urban heat island effect. By stripping away vegetation and laying down immense tracts of dark, opaque asphalt, human-made cities are literally overriding natural controls to create these isolated, heat-trapping microclimates. Thanks so much for exploring these atmospheric mysteries with me on this explainer. It leaves us with a pretty massive question. As our cities continue to grow, are we building our way out of the natural climate and into an entirely new set of extreme temperature rules?